3. Applying queuing theory. All right, the purpose of all of our previous discussion on the subject of probability and everything that was covered in there was really building up to the idea of, well, being able to answer interesting what-if questions and put numbers to problem solving so that we know, how many servers to buy or how much this or how much that we actually need. So let's do that. But first we're going to take a slight stop to discuss something called Little's Law. And Little's Law is a famous result of queuing theory that says the average number of systems is, well, just the average arrival rate in the system multiplied by the average time in the system. And we'll start with an open system. So E of n here, the expected value of n is the expected number of jobs in the system, is equal to lambda, the arrival rate, times E of t, the mean time that jobs spend in the system. So, for example, if a university takes an average of 5,000 students per year and each student spends an average of 4 years in school, there are 4 times 5,000 equals 20,000 students on average in university. Seems sensible. And the thing about Little's Law is that applies regardless of anything that we know about the system. We don't have to know anything about the arrival process. We don't, it could be Bernoulli, could be Poisson, anything. We don't have to know anything about the service time distribution, network topology, anything like that. Hopefully that result is somewhat intuitive. I mean, it seems maybe like it might be too simple to be true, but this is the case. I hope that your intuition leads you in that direction. If you wanted an explanation of, say, restaurants as a good analogy for this, think about the comparison between a fast food restaurant and a fancy-ish sit-down restaurant. On the one hand, we have McDonald's. This is a fast food restaurant. They make money by quick turnaround. So they get people in and out of the place quickly. Again, I guess I should preface this by saying, pretend it is in a time in which you are allowed to dine indoors at a restaurant, which is not true at the time of recording, but, pretend. One day it will happen again, and it's probably happened to you in the past that you've dined in a restaurant. So, okay, let's imagine that is an option at the time of discussion, and McDonald's wants to get people in and out quickly. They accordingly don't require a lot of seating. If you're there to eat at McDonald's, you're there, you eat your food, you get it, you go. That's it. And in fact, McDonald's kind of discourages you from staying. The chairs aren't that comfortable. As an example, it's a way of making it, subtle encouragement that you just eat and leave because it's not that comfortable. And so you should just get what you've come for and depart. On that account, they don't need a lot of seating because people don't stay very long, and therefore E of n, the number of people inside the restaurant at any given time, isn't actually all that large. Makes a certain amount of sense. On the other hand, a sit-down restaurant is that people leave slowly. You come, you stay for dinner, you stay for a significant period of time. Your intention there is to make an occasion of it, probably, meet with some friends, talk with them, have a nice time, stay a long time, buy another round, that sort of thing. And therefore, such a restaurant needs to have a lot more seating. And the example here is proof in the Delta Hotel, not too far from campus. And this is an example of a case where you would want a larger, if you will, seating capacity, because then you can serve more customers. Now, as a customer individually, this whole thing might seem a little bit strange. You want to enjoy your evening and you want to stay as long as you feel like staying. But from a restaurateur's perspective, they're eager to turn your table over, get you out of there so a new round of guests can be seated. Another way of thinking about that is that restaurants are in the business of renting seats, and the fact that you pay for food is not immaterial, but not the most important thing. So this gives you perhaps a a view of two different kinds of restaurant and how this would affect the expected number of people that you would find in there at any given time. Okay. Here's another way. If you wanted to think about it not in a restaurant analogy, but in a first-come, first-serve queue kind of analogy, you actually do something like this calculation frequently, I imagine. If ever you are waiting in line and you can see, okay, there are a few people ahead of you. In this case, you can count there are 5, and you notice that each person, it takes them, let's say, 2 minutes when it's their turn, and then the next person can go. And you can look at that and you can say, well, if each person takes about 2 minutes and there are 5 people ahead of me, I will multiply those things together. 5 times 2 equals 10. And that gives me an estimate for how many minutes I'm going to wait before it is my turn. Perfectly valid. This is to some small degree how you choose which checkout lane you want to get in at the grocery store or at Costco or something like that. Look at the lanes and count how many people are in it. You can even make an estimate of how long their service time is because you can probably see how much they have in their cart. And at that point, you're ready to go. You've decided, I think this lane is the shortest. You may be right, you may be wrong. The person ahead of you might have 3 items, but they feel a need to argue and insist that the store should honor the expired coupon from the competitor's flyer. That can happen. You don't like to see it, but it can happen. And if it happens, your estimate did not turn out to match exactly with reality. But of course, the goal of estimating is not promising that things will be exactly as they are. It is just taking your stock of the situation and making what is the best decision you can make under the information that you have. Okay, and so if the expected time for each customer to complete is 1 divided by lambda, because the average rate of completion is lambda, then we can approximate E of t as approximately 1 over lambda times E of n in this situation. For a closed system, the calculation is a little bit different. If there are n jobs in process at any given time, that's the multiprocessing level of the system, and you have x as your throughput rate. As long as your system is ergodic, and as per usual, we are not super interested in talking about systems that don't meet this criterion, then n is equal to x times E of t. All right. This assumes that there is 0 think time. So if E of t is the mean time that jobs spend in the system, multiply it by the throughput, and it gets you the multiprocessing level, although normally you know the multiprocessing level, so you would know, say, the n and x terms in this equation. Doesn't matter. When it comes down to it, with the information you have and the formula, you will be able to work out whichever of the fields you are missing. This does assume there's no think time, which is jobs are always ready and don't have to wait for silly users. And when you're presented with this kind of thing where I say, well, you'll have one of the things that you need and you'll have enough information to recover whatever else you need, this reminds me of something that one of my sister's instructors referred to as equation shopping. I think it was a physics course, and he actually wanted you to not go equation shopping. That you look at the problem and here are the 5 knowns and here's the 1 unknown. All right, and I want to find which equation on the formula sheet has those 5 knowns and 1 unknown. Those 6 terms total. And he referred to that as equation shopping, and he didn't like it. He said you should really try to understand the problem and know which formula you're looking for based on your understanding of the problem and not shopping the formula sheet. I don't really take that view. Go ahead, look for what you need, find what you need, take what you need. If you do it by browsing the formula sheet with your n knowns and n unknowns, honestly, that's what you would do in real life anyway. So there's no need to make your life harder. Did you solve the problem? Yes. Is the answer correct? Also yes. Great. Next problem. I don't want to be the teacher who's like, well, you didn't solve it using the method I wanted you to solve it with, so 0 points. Okay, if you do think about end users and think time, then you also would probably adjust your measure to care about the response time, E of r, instead, in which case, for a terminal-driven system, E of r is n over x minus E of z. E of z is the expected think time in that. If we have to do that, n is still the multi-programming level, x is the throughput, and then we have the mean time spent thinking. Okay. Probabilistic processes are described according to their models. And when we're talking about evaluating a system, we are looking at it as a probabilistic process. So there's some random chance that things arrive and random chance that things complete based on how long work takes and when work arrives. That's a probabilistic process, and those are the kinds of systems that we are broadly interested in. So we will consider one of the three models here. It could be deterministic. That is, the process is completely predictable and is characterized by constant factors. So if a new task arrives every minute, on the minute, then, all right, that is a deterministic process. Jobs arrive on a set schedule, and you can tell exactly when a job will arrive, and you can predict when the next one arrive with high accuracy, in fact, with total certainty, because we have defined the system such that that's how it happens. The other kind that we're interested in is the Markov process, and this is what is referred to as a memoryless process. That is, the future states are independent of the past history, and the future state depends really only on the present state. Those sound kind of contradictory, but they're really not. It's just, given a certain state, we can transition to future states with no problem, and it doesn't really matter very much what happened in the past. Wherever we are, we can get where we need to go. The third kind that's listed on there, G, is the general kind of process, and that one is completely arbitrary. I don't think we'll spend any time talking about that because it's just a little wacky. So we're really going to focus on Markov processes because they are nice, in some sense, and we really only have limited time here. This is not intended to be a whole course on queuing theory. It's just a module on it. And when we use a Markov process, it means that the number of arrivals follow the Poisson distribution. Inter-arrival times follow the exponential distribution, and service times also follow an exponential distribution. And this just says, like I say, our system is nice, again with nice in quotation marks for a certain definition of nice. It means that our system is something we can reason about and conforms to some parameters that make it possible to do that reasoning. All right, so these letters that we saw, the D, M, and G, are part of what is called Kendall notation. And Kendall notation is technically 6 symbols written in a specific order, separated by slashes, and the order is alpha, sigma, M, beta, N, Q. All right, so open sesame, secret password unlocked, access granted, welcome to the Matrix, Neo. Why don't we define those symbols? So the first one, alpha, is the type of distribution, and that's what we talked about earlier. Is it Markov? Is it deterministic? Is it general? It will be one of those things. Sigma is the type of probability distribution for service time, and then M, lowercase, is the number of servers that are available. Beta is the buffer size. N is the allowed population size, whether it is finite or infinite. And Q is the queuing policy. Turns out, in most circumstances, we just leave off the last 3, because if you assume there is an infinite buffer, infinite population, and first in, first out queuing, that's the default, and you can use the condensed form of Kendall notation where you just use the first 3 characters, in which case you have assumed the other 3. And those 3, well, really, I mean, we're going to choose Markov, I already said, for the first one, and we're also going to choose Markov for the probability distribution for service time as well, meaning the only thing that's really going to change under our scenarios that we will examine is whether it's one or many servers. Again, because this is not an entire course on queuing theory, we don't really have the time or bandwidth to go into a super long detailed discussion about all of the different meanings of the different options. we're trying at the end of the day to do a meaningful comparison of one server to many, or this many servers to that many servers. So really it's unsurprising that the dimension that will vary is the number of servers and really not anything else. So in your Markov process, we will produce MM1 and MMK. So MM1 means a Markov arrival process, exponential queuing system, and one single solitary server. When there are K servers, then we replace K with 1. So if there are 10 servers, it's MM10, something like that. Although, as per usual, we're interested usually in just comparing one versus many, or some number versus a larger number. That way we will come up with, hopefully, a meaningful result. Okay. What we'll calculate a lot of the time when we are interested in figuring out how our system is doing is utilization. And utilization is a fraction between 0 and 1, and it says that this is the amount of time that the server is busy. We introduced the concept of utilization earlier on, but I didn't actually give a formal definition of it, and now we have some tools with which to do that, and we can actually calculate it, and so utilization uses the symbol rho, and rho is lambda times s. Very good. It is the arrival rate multiplied by the service time. So that will give you, a very precise calculation of how busy the server is, and it's not that difficult a calculation to do, which is even better. No calculus needed. Okay. So given what we know, for an MM1 system, the completion time average TQ is S over 1 minus rho. So S being the service time, and then 1 minus rho is the how busy the server is. This makes some sense. If the server is completely busy, then rho is 1, and our actual completion time average is infinite, because we would have to wait forever, because the server is completely overloaded, and submitting this job means we hope one day it will get finished, but it never will. And if the server is not busy at all, there's nothing happening right now, utilization is 0, then there's no waiting, and the time to completion is just S, because S divided by 1 minus 0, so S divided by 1, so S on its own. And that means that there's no wait, so the completion time is just how long it takes for the work to run. It gets there, it's immediately its turn. By that same token, the average length of the queue, represented with W, is rho squared divided by 1 minus rho. Once again, if utilization is complete, the server is way overloaded, we're using 100% all the time, the average length of the queue is going to be infinite in that case, because we'll be, again, doing a division by 0 here. And if there's no work to do at all, then the queue is empty. So it is 0 divided by 1, so 0. And we can see that by looking at those extremes, our figures or our formulae are reasonable. They make sense at the bounds, right? If there's nothing to do, the queue length is 0. If we are completely drowning in work, then the queue length is infinite. That makes sense and is consistent with our understanding of the world. So our formulae look reasonable, and they seem reasonable as well. Okay, so let's do an example. We have a server that completes a request on average in 10 milliseconds. And again, I remind you that we always talk about averages. And the time to complete a request is exponentially distributed, and over 30 minutes, 117,000 jobs arrive. I told you there's only one server. I didn't say anything about more than one, so we know that it is 1. I've also said in the past that we are always going to deal with Markov arrival processes. So, okay, the first symbol in Kendall notation is also an M. And then it also says the time to complete a request is exponentially distributed, which is to say that sigma, the middle one, is M. So we have an MM1 situation. Using the formulae that we just saw on the previous slide, how long does it take to complete the average request, and what is the average queue length? We have our formulae. We know what to do. We can look them over again. So service time, we said, was 10 milliseconds, and the utilization row we can calculate using a formula from the previous slide, lambda times s. S we already know. And lambda we could work out based on over a 30-minute period, 117,000 jobs arrive. So service time is 0.01 seconds. Arrival rate is 65 requests per second. Just take the number of seconds in 30 minutes and divide 117,000 and you get 65. So we calculate the utilization as 0.01 times 65, which is 0.65. Aren't the numbers always so nice and convenient when we do this? And then using the above formulae, the TQ and W formulae, we get the time to complete the average request is 28.6 milliseconds, and the average length of the queue is 1.21. Sanity check. Do our numbers make sense? Do our numbers make sense? Okay, well, there's no way that the time to complete an average request could be anything less than 10 milliseconds, because even if the system was completely not busy at all whatsoever, then we would end up spending at least 10 milliseconds completing the request, which makes sense. So that's our lower bound. It couldn't be any lower than that. If we got a number that was lower than that, we did something wrong in the math. We have a problem. Okay, also the number is not infinite, but, good, fine, sure, whatever. Is the value of 28.6 reasonable? Well, let's look at the average length of the queue. The average length of the queue being 1.21 says there is, on average, at least one or two jobs ahead of us in the queue. And that means we correspondingly have to wait for those jobs to be finished before it will be our turn. And therefore, we expect that there will be a wait that is commensurate with the number of jobs ahead of us, and 28.6 milliseconds is, in fact, a reasonable amount of wait, given what we know. If you subtract 10 milliseconds from that, you're now at 18.6 milliseconds, and if processing a job takes 10 milliseconds, we're somewhere between 1 and 2. I mean, it's not exact because utilization is a bit higher than than 0 here, so there's some waiting involved. But our figures do appear to be reasonable. If you also want to calculate, say, the number of jobs in the system, the value capital Q gives us the average number of jobs, including in the waiting jobs as well as the ones that are being served. And remember, of course, this is an average. And if you want to find out what is the probability that there are exactly X jobs in the system at any given time, it's 1 minus rho times rho to the power of X. So if you want to ensure that you never get in a situation where there are more than 10 people waiting, if that's your trigger for spinning up a new instance, if there are 10 requests waiting, then looking at your utilization, you would say, all right, well, what is the chance that that happens? I don't know. Calculate it, figure out your utilization, and then calculate rho, which again being a fractional figure, will eventually be a small number if it's something to the power of 10, but there is a risk. If your utilization is high, we have a problem. Okay. So the probability that the number of jobs is less than or equal to n is then the sum of the individual probabilities, which is, if you're saying what is the probability that there are 10 jobs or fewer in the system, well, it's the probability that there are 0 plus the probability that there's 1 plus the probability of 2, and so on all the way up to 10. If you want to know what is the probability that there's more than 10 jobs in the system, you could do the sum from 11 to infinity, but don't. Just do 1 minus the calculation of what is the probability that it's 10 or fewer. Because sums to infinity are harder than finite sums. Maybe you're a real fan of mathematical summation, and you're like, oh no, I love summing to infinity. It's my favorite. But I am not. I prefer the approach where we do the finite sum. They seem more tractable to me, especially if especially if it's a large number and it's like, well, we'd have to do some sort of weird thing, and like when it comes down to it, if it's a finite sum, it might suck to do it, but if I'm not certain of my answer, if I think I might have done it wrong, I can always do it the hard way and, add up all 10 values and, check that I did it correctly, or add up all 50 values if for some reason I really need to be sure. Infinite sums feel a bit harder because counting to infinity takes a really long time. Okay. And coming up next, multiple servers.